This one is continuity from the right. Limit of f of x as x approaches a from the right equals f of a. Continuity from the right. This one is from the right, and this one is from the left. Good, I'm sharing my screen. Good, so let's start from left on the x-axis. Can we say anything about -4?
It looks to be continuous on either side, but it doesn't include the f of -4.
What type of discontinuity is that?
It's the removable one.
Awesome, that's it. The limit from the left and the limit from the right exist. They equal the same number, but they do not equal the function value at that point. Awesome. What about -2?
Would that be a jump?
Jump discontinuity. Very good. Awesome. What about 2?
Also jump.
Jump. Very good. What about 4?
Infinite.
Infinite discontinuity. Very good. Awesome. Infinite discontinuity.
It includes an infinite item. It's just infinite.
It doesn't matter because there is a vertical asymptote there.
Okay, thank you.
Very good. Okay, now continuous from the left, continuous from the right. We cannot talk about that at -4, but what about -2? Is this function continuous from the left or from the right at -2?
Left.
Yes, awesome, very good. What about at 2? Continuous from the left, continuous from the right, or none of the above?
Right.
From the right. What about at 4?
The right.
Very good, awesome. Okay, we got the idea, I think. Okay. What else? Yes, of course, our favorite. Piecewise defined functions. I think we are fed up with them already by now, but let's choose one more. And then show that f has a removable discontinuity at x equals 3 and redefine that. So we're going to choose 25 or 26. So a piecewise defined function. And then we can talk about or we can choose from here. That doesn't matter. So it's the same. All the questions are the same. Explain why the function is discontinuous at a given number. Sketch the graph of the function. And the next set right here is find the numbers at which f is discontinuous. The same thing. At which of these numbers is continuous from the left, right, or none of the above. Same thing. Exactly the same question. So I want to work on problems 43, 44, 45, one of them. And I would like to work on redefine a function to make it continuous everywhere if there is a removable discontinuity. And also one of these. Yep, that's it. That's all we really need. So let's start with the piecewise defined function. Which one? I'm sorry?
45.
45 it is. Let me copy it and then I'll stop sharing. So f of x, x plus 2 for x less than 0, e to the x. I'm sure you're going to very soon dream about these piecewise defined functions. I mean, this is probably the 4th or the 5th. Okay, good. First, we change these intervals so we know what's happening there. Can anyone give us the intervals?
So from negative infinity to 0.
Great job.
From 0 to 1.
with the bracket.
Yeah.
And 1 to, very good. Step 1, we have to present the domain. And step 2, we can start the table. Can anyone give us the domain?
Negative infinity to infinity.
Nothing is missing, no gaps. Awesome. Which values I have to put in the table? Which x values, to be exact, I have to put in the table?
0 and 1.
Absolutely. And some others, but 0 and 1 are key x values. Parenthesis and bracket, touching. Bracket and parenthesis, touching. Bracket, parenthesis, touching. First piece, second piece, third piece.
X plus 2.
Perfect.
Easily x.
Good. And 2 minus x. Good. Good. X plus 2. What value do you think is the best here? To the left of 0, of course.
Negative 2.
Of course. Why? Can anyone explain? It's the x-intercept. Awesome. Can you please plug in 0?
2.
Awesome. Right here inside parenthesis. Can you please plug in 0?
1.
Excellent. Well done. Can you please plug in 1? Yeah. Difficult to plot, but we'll find a way. Can you plug in 1 here and tell me another number that is nice, important?
Two minus 1 is 1.
Very good.
We could also use 2.
Exactly for the same reason. Awesome. Remember one more time, I'm going to use 3 different colors. Why am I using 3 different colors? Is because I want my students to remember that these cannot overlap. If I graph something like this, then I didn't understand anything about piecewise defined function. Please, 3 different colors. Okay, here they are. So this is number 3. You do not have, no one is asking you to use 3 different colors. I'm just trying to make a point. So negative 2, 0, and 0, 2. What type of point is 0, 2?
It's hollow.
Very good. And this is a line. Done with orange. Green now. 0, 1. What type of point is 0, 1?
Equals.
And then 1. And if you remember, this is almost 3. 1, 2, 3, a little bit lower. And what type of point is it?
Closed.
Very good. And remember, this is the exponential function. Do not graph it. Just this piece. Done. Next color. 1, 1. What type of point is 1, 1?
Open.
Very good. And then 2, 0. It's a line. One more time. They do not overlap. I have the orange, I have the green, I have the red. There is absolutely no overlapping between the 3 colors. Otherwise, this will not be a function. If this is full, this has to be open. Otherwise, it will not be a function. If this is full, this has to be open. Okay, since we want also number 4, we need to get used to it and determine the range. Can anyone give us the range of this function?
Negative infinity to E.
That's it. That's it.
Doesn't the last function, the red one, need an arrow at the end to show that it's going to?
Oh, yes, of course, of course. Sorry, I'm sorry. Yes, thank you. Thank you.
It's minus 2 points, by the way.
Minus 2. It should be minus 4, actually. But thank you. Now, if I look at this and I ask you, what is the limit as x approaches 0 from the left? See how important this graph is, this table is? More than the graph, actually. Limit from the left of 0, what is it?
2.
2. Limit from the right of 0.
1.
1. Limit from the left of 1.
E.
And limit from the right of 1.
1.
That's it. I'm begging you to understand this table because I'm going to add 2 more rows to this table in this class. So this is a super important table. Okay. Now, what type of discontinuity? Obviously, there is a discontinuity at 0. So at x equals 0.
A jump.
Jump. At x equals 1.
Jump.
Jump. Does this function have a removable discontinuity?
No.
No removable. Is this function ever continuous from the left?
Yes.
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 Where?
At 2.
Continuous from the left, wouldn't that be a 1?
At 1. Very good.
Oh.
Continuous from the right. Is this function continuous from the right? Anywhere?
Yes. At 0.
Yes. At x equals 0. I meant to write continuous from the right. I'm going to put in parentheses right. Sorry about that. I tried to squeeze everything in this little spot. Very good. There is nothing else we need to know. This is it. But I already knew this from here, that this is a jump, this is a jump. The limit from the left, limit from the right, I have everything. The brackets are very important because the bracket is a full point. The parentheses are very important because the parentheses are an open point. So please stick with me with this table. Okay, I'm going to share my screen again. And let's take a look, which page am I on? I'm on page 6. Okay, 6. Okay, so this was done. I want to come back here. Show that f has a removable discontinuity at x equals 3. Redefine f of 3 so that f is continuous at x equals 3. Okay, let's look at 25. And this is f of x, x minus 3 over x squared minus 9. Okay. Good. So can anyone, first of all, tell us how to factor the denominator? That's the key here.
X plus 3, x minus 3.
We have to state the domain before we try to simplify the function. That's why I covered the top. Do not touch anything before we state the domain. So, can anyone tell us what is the domain of this function? What do I have to exclude?
Positive
3.
and negative 3.
Awesome. In other words, the domain is this. Union negative 3, 3, union 3 to infinity. So make sure you don't exclude anything else but positive and negative 3. Good. Now, I am allowed to do this. After I state the domain, I state the restrictions, and now I can write 1 over x plus 3. So the simplified form of this function is 1 over x plus 3, right? But I would like to see not at what happens at negative 3, but what happens at 3. So when x equals 3, there is what is called a hole in the graph. And I'm sure you're going to ask, and I would ask too, why? How do you know? How do you know that x equals 3 is a hole in the graph? See, notice that x plus 3 stays in the simplified form. Still, x cannot be negative 3, but because it stays in the final form, this is a vertical asymptote. The factor that goes away is not a vertical asymptote. It's gone. Because it's gone, it will change into a hole in the graph. The factor that still stays all the time till the end, or stays in the simplified form, that will be a vertical asymptote. So we could say that we can determine a new function that is based on the original function with x minus 3 over x squared minus 9, of course, with x not equal plus or minus 3. And if we want to make this function continuous at x equals 3, we have to define this. So I'm going back for a second to redefine so that f is continuous at x equals 3. The function will not be continuous everywhere. I just thought that they had an error there, but they don't. They only want us to create a function that is continuous at x equals 3, not a function that is continuous everywhere. I just wanted to check that. Okay, so the question is, how do I define this function? Remember the hole in the graph. Hole in the graph. How did we call it a few minutes ago?
Discontinuous.
Right?
Yes.
Right. So the hole in the graph is a removable discontinuity. As long as I can show that the limit from the left and the limit from the right are the same, and they equal the function value here, then so if they are the same, it's removable. But now I want to define this and fill it in. So what is the limit from the left of 3 of the simplified form, and the limit from the right of 3 from the simplified form? So now our simplified form is this. All I have to do is find the limit from the left of 3 and the limit from the right of 3. So what is the limit? Of course, they have to be the same. It's a hole in the graph. This must equal that. So limit as x approaches 3 from the right of 1 over x plus 3 will equal the limit as x approaches 3 from the left of 1 over x plus 3. And this is what I need to write in here to make it continuous at 3.
It'd be 1 over 6, right?
That's it. That's it. So this function will never be continuous at negative 3. It's a vertical asymptote. But it's guaranteed to be continuous now. This new function we created from the original function, just change one value. Continuous at x equals 3. Guaranteed. But I can never say that this function will be continuous everywhere. They only wanted us to determine what is the point that we have to fill in. So the limit from the left, limit from the right are 1/6. So then the function value at 3 has to be 1/6. And now this function is continuous at x equals 3. I'm sharing my screen.